For the next few videos, I want to talk to you about geometric sequences. Another word for geometric is exponential. An exponential sequence and a geometric sequence, those two words are interchangeable. These sequences are really important for when we move on to financial maths. When we study financial maths, almost every financial maths question involves a geometric sequence. So the first thing I want to do, let's just go through a few examples of geometric sequences. The first example we could come up with is just something like, supposing we had 1, 3, 9, 27, 81. All I'm doing there is I'm multiplying by 3 every time. In a geometric sequence, there's a constant multiple, or what we refer to it as a common ratio. The things, when we're dealing with arithmetic sequences, we have to talk about A and D. Here we have to talk about A and OR. Where A is the first term, in this case it's clearly 1, and OR is the common ratio. In order to work out your OR is any term divided by the previous term. So for example, Tn plus 1 divided by Tn. Any term divided by the previous term. It is not any term divided by the next term. It's dividing by the previous term. So in this case, I could take any term in this sequence, let's say 27, and divide it by the previous term. If 27 divided by 9 is the same as 81 divided by 27, is the same as 9 divided by 3, which is the same as 3 divided by 1. No matter what way I do it, in this case the common ratio is 3. So what we're dealing with in these questions is where in arithmetic sequences we wanted to find A and D, in geometric sequences we want to find A and OR. But just make note of the fact that the common ratio is any term divided by the previous term, not the next term. Another type of sequence I want to just show you as well is, obviously these sequences could be decreasing as well. I could give you 32, 16, 8, 4, 2, 1, a half, and so on. Clearly what I'm doing there is I'm multiplying by a half every time. If we were to work out the common ratio for this one, it's any term divided by the previous term. For example, 16 divided by 32. In this case, the common ratio is a half. And in this case, obviously, my A is just 32. So for a sequence like that, A is 32 and your OR is a half. If you go to page 22 in your maths tables, there's 3 formulae for geometric sequences on the bottom of page 22. In this video, I want to practice using the formula for Tn and the formula for Sn. We'll wait for the moment, and in a few videos time we'll talk about S infinity. I want to just talk about the first 2 formulae for geometric sequences in this video. Okay, suppose I give you the geometric sequence 2, 8, 32, 1, 2, 8, 5, 1, 2. I could ask you to find the general formula for the geometric sequence above. If you're asked to find the general formula, you should note that on page 22 in your maths tables, the general formula for a geometric sequence is A OR to the power of n minus 1. So in this case, to find my A, it's just the first term, it's clearly just 2, and OR is any term divided by the previous term. In this case, I took the second term divided by the first term, and I got 4. You can clearly see that all we're doing each time is multiplying by 4 anyway. But now I know A and I know OR, I can sub in to get the general formula. The general formula for this geometric sequence, well, instead of A, I would put in 2, and it's A multiplied by OR, which is 4, to the power of n minus 1. Now, I just want to point something out to you here. Often when I do this in class, students try to go further and multiply the 2 by the 4 and get 8. You are not allowed to do that. 4 to the power of an unknown, you just avoid it. You cannot mathematically multiply the 2 by the 4. In a scenario like this, if you have 4 to the power of an unknown, you're better off to just leave it as it is. In order to find the value of n, we often have to use logs. Because remember from algebra, if the unknown is in the power, we introduce logs so we can bring the power in front. But if I asked you to just get Tn, you're better off to just leave it like that. Let's have a look at the other formula now. Supposing I asked you to find Sn, the sum of the first n terms of the sequence. Remember, like for example, S5 is the first 5 terms added together. If you're asked to find S5, it would actually be easier to just add 2, 8, 32, 1, 2, 8 and 5, 1, 2. But supposing we were just asked to get that Sn. We've already worked out that A is 2 and that OR is 4. So if I asked you to find Sn, you could just sub in. A in this case is obviously just 2 times 1 minus 4 to the power of n. And that would all be divided by 1 minus or in other words 1 minus 4. Now, you're better off not to multiply out this bracket. What I would suggest here, if you to just simplify it, I would leave it as 2 times 1 minus 4 to the power of n over minus 3. If you were just asked to get Sn, as far as I'm concerned, you should leave it like that. I just want you to be aware that it is possible to multiply out the bracket here. 2 by 1 is 2, and 2 by minus 4 to the power of n is minus 2 times 4 to the power of n. But it's almost kind of messier written like that anyway. The problem is you cannot multiply the 2 by the 4 to the power of an unknown. So as far as I'm concerned, you're better off to leave it like that. What you could then do is, the chances are you'd probably be asked to find S5 or something like that. Supposing I asked you to find S5. That just means wherever there's an n, you sub in a 5. In this case, it would be 2 times 1 minus 4 to the power of 5. And if we plug this into our calculator, we can get a value for S5. So S5 works out as 682. Just be aware there, obviously you could use that formula, but it probably would be easier if you're asked to get S5 to just add the first 5 terms together. If you add those 5 terms together, you get 682. But obviously if you're asked to get like S100 or S1,000,000 or S of a large number, it's much easier to just use the formula. So now that we've just subbed into the formula, I want to give you a few questions to try using Tn and Sn. Okay, part A here was very straightforward. I just asked you to find A and to find OR. A just refers to the first term, in this case 80. And in order to work out OR, the common ratio, it's any term divided by the previous term. So 5 over 10 or 10 over 20 or 20 over 40 or 40 over 80, in each case you're going to get a half. So for the rest of this question, A is 80 and OR is a half. Okay, so once we have A and OR, to get the general formula for the sequence is relatively straightforward. In page 22, it tells me the general formula Tn is equal to A OR to the power of n minus 1. So all you're required to do is, instead of A, you sub in an 80, instead of OR, you sub in a half. I could say that Tn is equal to 80 times a half to the power of n minus 1. But I'm not allowed to multiply the half by 80, because it's a half to the power of an unknown, which means for the moment I want to avoid it. In the next part of the question, now I'm asked to find T10. All I have to do is sub in 10 instead of n, and I'll be able to work out what is the 10th term in this pattern. So C said, hence find T10 in terms of A over B. I had Tn was equal to 80 times half to the power of n minus 1, so just instead of an n, you sub in a 10. 10 minus 1 is 9, and if you plug that into your calculator, the 10th term in this sequence must be 5 over 32. Obviously, it is acceptable in a question like that to actually just continue on your sequence. Just if you just kept multiplying by a half each time, you would work out what the 10th term is, and it would have worked out as 5 over 32. Part D was probably the trickiest question I gave you here. It says find the smallest value of n for which Tn is less than 0.01. Remember, Tn refers to the term. If I subbed in 5, I get the 5th term. If I sub in 4, I get 10. If I sub in 3, I get 20. So I want to know what value do I need to sub in order to get a number that is smaller than 0.01. Or in other words, if I just continue this pattern on, how many terms are there before you get to a number smaller than 0.01? Now we can do this mathematically. In part B, we worked out that the general formula for this sequence is 80 times a half to the power of n minus 1. And I want to know what is the value of n for which this will be less than 0.01. So mathematically I could just write that out as, I want to know when is this general formula, I want to know when is it less than 0.01. However, just like in the arithmetic sequences, I think these questions are easier if you ignore the inequality for the moment. Work out a value for n for which the general term is equal to 0.01. And then at the very end, just work out whether you have to round up or whether you have to round down. In this case, in order to solve it, there's an unknown in the power, so we're going to have to introduce logs. But before I introduce logs, I need to isolate the part of the term that has the unknown. Or in other words, I need to isolate the half to the power of n minus 1. So before we introduce logs, we would have to divide both sides by 80. If I divide 0.01 by 80, I get 1 over 8,000 is equal to a half to the power of n minus 1. And now your unknown is in the power, and in order to eliminate the power, we first need to introduce logs. So we can introduce ln, the natural log, in front of both sides. I can introduce ln in front of the left-hand side and ln in front of the right-hand side. Remember that the whole point of introducing logs is so that now we can apply the rules of logs. If you look at page 21 in your maths tables, in the column in the middle are the rules for logs. The third rule of logs says that if you have log of something to a power, you can just bring the power in front. So I can simplify the right hand side here as n minus 1 times ln a half. And now I'm in a really good place because notice the powers are gone. There's no more unknown in the power. The left hand side for the moment, I'm still just going to leave it exactly as it is. Now my goal now is just isolate my n. Obviously the first thing I could do here is I could multiply out the right hand side. I'll leave the left exactly as it is, but the right hand side it's n times ln a half, so it's n ln a half, and then it's minus 1 times ln a half, which is clearly just minus ln a half. At this stage it's just basic algebra. I'm trying to isolate the term with the n in it. So what I'm going to do is the second term here, ln a half, I'm going to add that to both sides so that it's eliminated from the right hand side. I can now say that ln of 1 over 8,000 plus ln of a half is equal to n ln of a half. Now I'm running out of space, so I need to continue this one up at the top. So make sure you take this down before we move on. So this is where I left you. We had just managed to isolate the term with the n. Now in order to get n on its own, we need to divide both sides by ln a half. If you divide the right hand side by ln a half, you're just left with n. If you divide the left hand side by ln a half, you have ln of 1 over 8,000 plus ln a half divided by ln a half. And if you plug all that into your calculator, you end up with 13.9658. So I know that the 13.9658 term would be equal to 0.01. Obviously in a scenario like this, your value for n has to be a whole number. And I've worked out that if it's after 13.9, it'll be 0.01. I want to know when does it go beyond that. I want to know what is the first term that is less than 0.01. So obviously the 13th term is greater than 0.01. But if I continue on, the 14th term is the first term that will be less than 0.01. So in this case, your answer would be that the 14th number in this sequence is the first number that is smaller than 0.01. So again, notice there how I ignored the inequality and just used it as an equals while I was doing the equation. And at the end, I think about the implications of the inequality when I have the value. A lot of these questions are going to end up as logs questions because, as you can see in the formula for Tn and the formula for Sn, the n is in the power. So if you don't know n and you're looking for it, it's a logs question where you have to introduce logs in order to eliminate your power. There's two bits of theory we're looking at in this video. The first one is in order to prove that 3 terms are in geometric sequence. If I asked you to prove that 3 terms are in geometric sequence, you'd have to prove to me that the third one divided by the second one is equal to the second one divided by the first one. Or in other words, that there's a common ratio. You can see from all the ones we dealt with in the previous video, that would always have been the case. That's different and distinct from proving that a sequence is geometric. Just because the first 3 terms are in geometric sequence doesn't necessarily mean that all of the terms are in geometric sequence. In order to prove that the entire sequence is geometric, you have to prove that any term divided by the previous term is a constant. Or in other words, the Tn plus 1 divided by Tn. Where Tn plus 1, that might be term number 10 divided by term number 9. That could be any term divided by the previous term. So you have to actually sub in n plus 1 in n, and when you divide the previous one when you divide Tn into Tn plus 1, it should work out as a constant. So I want you to notice how this mirrors the video we did in arithmetic sequences, where we had to prove 3 terms were in arithmetic sequence and we had to prove a sequence was arithmetic. For this video, we're going to explore this theory and do a few questions on it. If I gave you a question that said that the general formula for a sequence is Tn equals 5 times b to the power of n, where b is a constant, I could then ask you to prove the first 3 terms are in geometric sequence. Before I can prove the first three terms are in geometric sequence, I obviously need to find the first three terms. To find the first term, I'm looking for t1, I would just sub in 1. It would be 5 times b to the power of 1, or in other words just 5b. The second term in this case would be 5b squared. And the third term in this case would be 5b cubed. So they're your first three terms. Once you have your first three terms, we can now worry about proving that they're in a geometric sequence. If three terms are in geometric sequence, that means that they have a common ratio. Or in other words, it means that the third one divided by the second one will be equal to the second one divided by the first one. So if I sub that in here, the third one is 5b cubed and the second one is 5b squared. The second one is 5b squared and the first one is just 5b. Now in this case, the 5 in each case is going to divide, 5's divide into the 5's on the bottom divide into the 5's on the top. B squared divides into b cubed b times, and b divides into b squared b times. So I'm left with b on the left and b on the right. So in this scenario, clearly the first three terms are in geometric sequence. But let's look now at what we would do if it asked me to prove this sequence is geometric. Okay, in order to prove that the sequence is geometric, I need to prove that any term generalized, as in tn plus 1, divided by the term before it, which would be tn, that will always give me the same thing. Or in other words, that is equal to a constant. Remember, term n plus 1 refers to the term directly after term n. This tn refers to term number n, tn plus 1 refers to term number n plus 1. If any term divided by the previous term always gives me a constant, I can say that for any value of n, that this sequence is geometric. But obviously before I can do this, I already know what tn is, but I need to get tn plus 1. To get tn plus 1, I can just sub into the general formula. Tn plus 1 must be 5 times b to the power of n plus 1. So now I know tn plus 1, I can sub in here and hopefully end up with a constant. Remember, they told me that b is a constant, and obviously 5 is a constant, so the only thing I'm dealing with at the moment that is not a constant is the n. So when I sub in here, I've got 5b to the power of n plus 1 divided by 5 times b to the power of n. If I can somehow eliminate the n's, then all I'm left with is a constant. Well, first of all, the 5 divides into the 5 once, and they're more or less gone. All I'm left with is b to the power of n plus 1 divided by b to the power of n. I can simplify the top of this fraction, because the first rule of powers on page 21 in your maths tables says that a to the power of p plus q is the same as a to the power of p multiplied by a to the power of q. With that in mind, I can say that b to the power of n plus 1 is equal to b to the power of n multiplied by b to the power of 1. The bottom I can leave exactly as it is at the moment, and now I'm in a good place because clearly the b to the power of n on the bottom will divide into the b to the power of n on top, and all I'm left with is b. So, and I was told in the question that b is a constant. Remember, the whole point of this question was to prove that tn plus 1 over tn is equal to a constant. It doesn't matter what the constant is. I've now proven that for no matter what numbers I sub in for n, if I subbed in 199, the difference between, or the common ratio between them would be b. If I sub in 1,999,999, the common ratio between them would be b. No matter what I sub in for n, the common ratio is always b. Okay, so I want to give you two questions based on this theory. The first one says that the first three terms in a geometric sequence are x, x plus 5 and 7x plus 5 respectively. In other words, this is t1, t2 and t3. And it says find x, where x is greater than 0. So you need to realize that if these three terms are in geometric sequence, that means that the third one over the second one equals the second one over the first one. But in these questions, when you solve that, you're going to end up with a quadratic, which means there's two possible values of x. There's two numbers I could sub in for x that would generate a geometric sequence. But in this question, they've told you they only want the positive one, where x is greater than 0. Once you've worked out your x, you should be able to then find t4, the fourth term in the sequence. The second question here says that the first three terms in a geometric sequence are 2x minus 4, x plus 1 and x minus 3, respectively. So this is T1, T2 and T3. With that in mind, they've asked you to find the two possible values of x. So I want you to take these down and work through them and then watch my solutions on it. Okay, in question 1 here, it tells me that the first three terms in a geometric sequence are x, x plus 5 and 7x plus 5. It says find x if x is greater than 0. You need to hone in on the fact that the three terms given are in a geometric sequence. If they're in a geometric sequence, you know that the third one over the second one must be equal to the second one over the first one. Or in other words, there's a common ratio involved here. I know that T1 is x, that T2 is x plus 5, and that T3 is 7x plus 5. So if I just sub in, now I've got one equation and one unknown, I can just solve this and find the value of x. Okay, so this is relatively straightforward now. In order to eliminate my fractions, I multiply by the denominators. And I get x times 7x plus 5 equals x plus 5 by x plus 5. If you multiply this out and move everything to one side, you end up with a quadratic equation 6x squared minus 5x minus 25 equals 0. If you factorize and solve this, you get x equals minus 5 over 3 or x equals 5 over 2. In other words, there's two possibilities here. Given the three terms we were given, which was x, then x plus 5, then 7x plus 5. If you sub in minus 5 over 3, or if you sub in 5 over 2, those three terms will have a common ratio. So either of these x values will generate a geometric sequence, will generate three terms in geometric sequence. But I've been told that I want the value of x that is greater than 0. So I'm going to eliminate this one because it's not the one I'm looking for. So your final answer for that is you've worked out that x is 5 over 2. But now what we need to do is sub in to find the first three terms, because the second part of this question asked me to work out what is the fourth term. So if I sub in x is 5 over 2 into the three terms I know, I'll be able to figure out what the next term in this sequence would be. Okay, by working out x is 5 over 2, I could now say that the first term, which was just x, is 5 over 2. The second term, which was x plus 5, would be 15 over 2. The third term, which is 7 times x plus 5, would be 45 over 2. So I can clearly see my sequence now. They're all over 2. The first one is over 5. The second one the first one is a 5 as a numerator. Second one 15. The third one 45. I can clearly see that I'm just multiplying. 5 by 3 gives me 15. 15 by 3 gives me 45. So to work out what the fourth term, T4, is, I just multiply 45 by 3. 45 by 3 is 135. So that means the fourth term must be 135 over 2. Sometimes you can just look at it and you can figure out what the answer is. But that won't always be the case. If you're not able to just look at it and figure out what the answer is, the alternative is you work out the common ratio. The common ratio in this case is any term divided by the previous term. Or in other words, it would be 15 over 2 divided by 5 over 2. If you put 15 over 2 and divide it by 5 over 2 in your calculator, you'd get 3. And that tells you that to go from any term to the next term, you just multiply by 3. So ultimately, that's all we were doing. The first term by 3 gives me this. The second term by 3 gives me this. The third term by 3 gives me the fourth term. So that's how I know the fourth term in this sequence would be 135 over 2. Okay, question 2 is more or less the same as question 1. I've told you the first three terms in a geometric sequence are 2x minus 4, x plus 1 and x minus 3 respectively. Now this time I want you to find the two possible values of x. If the three terms are in geometric sequence, I know the third one over the second one equals the second one over the first one, because a common ratio must exist. So all I did was sub in. T3 is x minus 3, T2 is x plus 1. T2 is x plus 1 and T1 is 2x minus 4. And at this stage, I've got one equation and one unknown, which means I'll be able to find the two possible values of x. So I can simplify this one more or less the same way as I simplified the previous one. I multiply both sides by the denominator to eliminate the fractions, and then I move everything to one side and I ended up with a quadratic of x squared minus 12x plus 11 equals 0. If I factorize it, I get x minus 1 times x minus 11, which means the two possible values for x are x equals 1 and x equals 11. And then usually in an exam question, depending on the way it's worded, you would either be taking x equals 11 or x equals 1 as your answer. But in this case, I asked you for both of the values, so it's acceptable to have either one here. So that's all I want to do on this specific bit of theory. What we need to do now is move on and talk about something else to do with geometric sequences. Okay, I want to talk to you about another bit of theory in geometric sequences now. What I've done is I've just drawn out a geometric sequence here. Clearly by looking at this one, you can tell that the first term in this geometric sequence is -1. And to work out the common ratio, it's always any term divided by the previous term. In this case, any term divided by the previous term, for example, the second one divided by the first one gives me -3. In other words, to go from any term to the next term, you're just multiplying by -3. So what I want you to think about now is it's something similar to what we did in arithmetic sequences. The first term in any geometric sequence is always just referred to as A. Now I want you to ask yourself, what do you do to the first term in order to get to the second term? In order to get to the second term here, I multiply by -3. Or in other words, I multiply by whatever the common ratio is. Which means that in any geometric sequence, the second term is always the first term multiplied by the common ratio, or A times OR. What do I do to get from 3 to -9? Clearly what I've done is I've multiplied by the common ratio again. 3 by -3 gives me -9. So I can say that the third term in any geometric sequence is A OR multiplied by OR. Or in other words, A OR to the power of 2. The fourth term, if I continue on, I just multiply by OR again. So the fourth term would be A OR to the power of 3. So the first term is A OR to the power of 0, the second one is A OR to the power of 1, the third one is A OR to the power of 2, A OR to the power of 3. So that means that the 10th term must be A OR to the power of 9. The 50th term must be A OR to the power of 49. The 100th term would be A OR to the power of 99. What I want you to figure out is what is the nth term. The nth term in any geometric sequence would be A OR to the power of one number less than n. Or in other words, n minus 1. The 10th term is one number less than 10, so that's a 9. The nth one would be A OR to the power of n minus 1. So I want you to realise here that what I've just arrived there, that's actually the general formula for a geometric sequence. That's available on page 22 in your maths tables. It says Tn, the nth term of any geometric sequence is A OR to the power of n minus 1. We can use this theory now to answer a lot more questions on geometric sequences. Okay, so we can use that theory to answer a question like this. If I was told that I have a geometric sequence where the second term is 8 and the fifth term is 27, I can now find A and OR. I know that in any geometric sequence, the second term is A multiplied by OR to the power of 1. And they've told me that here the second term is actually 8. So I can say that A OR to the power of 1 is equal to 8. Now I also know from the theory at the start of this video that the fifth term in any geometric sequence would be A OR to the power of 4. And they told me here that the fifth term is actually 27. So at this stage, I want you to recognize that we've two equations and we've two unknowns, which means we should be able to work out the value of A and the value of OR. Now in this case, because you're multiplying the A by the OR, you have to solve this simultaneous equation by substitution. What you should do is go to the simpler equation and isolate one of your letters. What I want to do here is I want to take the first equation and I want to isolate my A. Because if I isolate A, I can sub in whatever I get into the second equation, and I'll have one equation with only one unknown, and I'll be able to find the value of OR. So if A multiplied by OR is equal to 8, in order to isolate A, I would divide both sides by OR. And I could say that A is equal to 8 over OR. And at this stage now, I know that instead of A, I can just sub in 8 over OR. So if I go back to my second equation now, instead of A, it would just be 8 over OR. And I'd multiply that by OR to the power of 4, and it's equal to 27. At this stage, I want you to recognize that we've one equation, we've one unknown, which means we've enough information, we'll be able to find the value of OR. Now I want you to realize that this is, on the bottom, this is an OR to the power of 1. If you were multiplying 8 over or by or to the power of 4, that's like or to the power of 4 over 1 by 8 over or to the power of 1. One of the ors on the bottom divides into one of the ors on the top. So or divides into or to the power of 4, and I'll be left with or cubed. Which means the left hand side is actually just 8 or cubed is equal to 27. Now obviously my goal here is to isolate or. If I isolate or, I have to divide both sides by 8. And I could say that or cubed is equal to 27 over 8. Now if I know or cubed, in order to get or on its own, I need the cubic root of both sides. But this one is actually relatively straightforward to do. The cubic root of 27 is just 3, because 3 by 3 by 3 is 27. And the cubic root of 8 is just 2, because 2 by 2 by 2 gives me 8. So the cubic root of 27 over 8, obviously you could plug it into your calculator, but it works out as 3 over 2. Now that I have a value for or, I can sub back in and I can work out a value for a. Clearly the easiest thing to sub back into is this. I know that a is equal to 8 over or. But now that I know or, I can actually say that a is equal to 8 divided by 3 over 2. Now in maths, I would advise you to always avoid something like this. 8 divided by a fraction makes life much harder. Instead of dividing by 3 over 2, you can flip the fraction and multiply. 8 divided by 3 over 2 is the same as 8 multiplied by 2 over 3. You just flip, you get the reciprocal of the fraction and you multiply. And now this is relatively straightforward. We can do it in our heads. It's 8 over 1 by 2 over 3. We just multiply the top by the top and the bottom by the bottom. 8 multiplied by 2 is 16. 3 multiplied by 1 is 3. So in this case, your a, the first term in this geometric sequence, is 16 over 3. And the common ratio is 3 over 2. And that would be your final answer in a question like this. Okay, so I want to just practice one question based on this theory. Supposing I told you that in a geometric series, the 5th term was plus 128 and the 10th term was plus 4. With that in mind, I want you to find the value of a and the value of or. So I want you to pause the video, work through this question, and then watch my solutions on it. So in order to start this one off, you need to realize that in a geometric series, the 5th term can be described as a by or to the power of 4. And in this specific series, I know that that is equal to 128. The 10th term is a by or to the power of 9. And in this case, that's equal to 4. And at this stage now, I have two equations and two unknowns, so I can find the value of a and the value of or. Okay, so once again, we have to use substitution. What I decided to do here was to take the first equation and isolate my a. If I'm going to isolate a, I divide both sides by or to the power of 4. And I work out that a must be 128 over or to the power of 4. And now I can go back to my second equation, and instead of an a, I can sub in 128 over or to the power of 4. Now at this stage, you should realise that or to the power of 4 divides into or to the power of 9, and you're left with an or to the power of 5 on the top. Or in other words, we can just subtract the powers, the top power minus the bottom power. 9 minus 4 gives me 5. So I can say that 128 or to the power of 5 equals 4. In order to get the or term on its own, I would divide both sides by 128. And I can say that or to the power of 5 is 4 over 128. Now if you know or to the power of 5, in order to get or, you need to get the 5th root of both sides. So that's a small 5 in front of what looks like a square root sign. So the 5th root of 4 over 128, if you plug that into your calculator, or works out as a half. Once I know the common ratio for this geometric series, I can sub back into one of the original equations and I can find the first term a. I decided to sub into this. I know that a is 128 over or to the power of 4. So if or is a half, I can say that a is 128 over a half to the power of 4. If you plug that into your calculator, you'll work out that a must be equal to 2048. So now you know the first term, you know the common ratio. The question could go further and they could ask you to find the 10th term, find the 50th term, find the sum of the first 12 terms. So they could ask you any amount of questions now Because now that you know A and OR, you can just use the formula in your maths tables to solve anything else that they asked you. So that's all I want to talk about on this specific type. All we need to explore now are questions on the sum to infinity of a geometric series. And once we've the whole lot done, we can start to amalgamate questions like this with sum to infinity questions as well. Okay, the final new thing we need to explore in sequences and series is to get the sum to infinity of a geometric series. The formula at the bottom of page 22 in your maths tables, it's actually the easiest formula of all. It's just A over 1 minus OR. If you have your A and you have your OR, it's very simple to sub into. What I've listed out here are 3 different geometric series. Only one of these has a sum to infinity. So I want to talk to you about a bit of theory here. The first one here is I've 16, then 8, then 4, then 2, then 1, then a half. Clearly all I did there was I multiplied by a half every time. If I keep multiplying by a half, the number gets smaller and smaller and smaller. The next one will be 1 over 16, 1 over 32, and so on. It just keeps on getting smaller. The sum to infinity refers to the sum of all of the terms. If I added up all of the terms, if this went on indefinitely, if this goes on forever, what are all of these terms going to add up to? So I want you to notice here that I want you to think about what would happen to this sequence if it went on indefinitely. If it went on for another hundreds of billions and billions and billions of terms, eventually the number would be so ridiculously small that it might as well be 0. So because these numbers are getting smaller, because these numbers are getting closer to 0, if this went on forever, the number that I'd be adding on each time, it might as well be 0. It would be so small that it might as well be 0. So because these numbers are getting closer to 0, or they're decreasing, it's approaching 0, that means that a sum to infinity exists for this sequence. Because the numbers are approaching 0. In this case, I could just say that A is equal to 16, and OR is any term divided by the previous term. In this case, OR would be 8 over 16, or 4 over 8, or 2 over 4. It's going to be a half. So if I got the sum to infinity for this first geometric series, or sequence, the sum to infinity of this sequence would be A, which is 16, over 1 minus OR. Or in other words, 1 minus a half. And if you plug that into your calculator, you're going to get 32. If this sequence goes on forever, the sum to infinity is 32. But I want you to realize that it will never actually get to infinity. It will just keep on going. It'll never actually reach infinity. Infinity is undefined. What it actually means is if you added up all of these terms, if you added up the first billion terms in this sequence, it would be equal to 31.99999. It would be a number that's really, really close to 32, but it'll never get to 32. Okay, so I want you to look at this second one here. I started with 1/8, multiplied it by 2 and got a quarter, multiplied it by 2 and got a half, multiplied by 2, just kept on multiplying by 2. I get 2, 4, 8, 16, I'd get 32, 64, 128, it would just get bigger and bigger and bigger and bigger and bigger. Imagine what would happen if this series went on indefinitely. If I just kept on multiplying by 2 for an infinite amount of values, eventually the number would be so ridiculously big that it might as well be infinity. If this goes on forever, the sequence, it has no limit. If this goes on forever, the numbers are approaching infinity. There's no limit to this one. So because the numbers are going further away from 0, because it's getting bigger there, you cannot get a sum to infinity for that one. I want to just go through something here. Clearly the first term here is 1/8. The common ratio in this case is 2. Because the common ratio is 2, this time we cannot get the sum to infinity of this geometric series. And this one is a similar example. This time I'm multiplying by 2 again. I started with minus 1/8, minus a quarter, minus a half, minus 1, minus 2, minus 4. So I want you to realize these numbers are decreasing, but they're getting further away from 0. If this sequence went on forever, eventually it would just be minus infinity. It would be the number is so ridiculously big that there's no limit to if you added up all of these terms. So you cannot get a sum to infinity for that one, and you cannot get a sum to infinity for that one. I want you to look in the bottom right hand corner of page 22 in your maths tables. Beside the sum to infinity formula, it tells you that you can only use this formula if the absolute value of OR is less than 1. Mathematically, another way of saying that is saying that OR needs to be between 1 and minus 1. If the common ratio in a geometric series is not between 1 and minus 1, then you cannot get the sum to infinity. You'll be able to recognize it, like if the numbers are getting closer to 0, you'll be able to tell, oh, I can get the sum to infinity for that one. But this one has a common ratio of 2. This one also has a common ratio of 2. If the common ratio is bigger than 1 or less than minus 1, you cannot get the sum to infinity. So I just want to really highlight that. You have to be careful. It only works if the numbers are approaching 0. So let's try a few questions now based on that theory. Okay, so I'm giving you 2 questions in this video that kind of joins up a lot of the stuff we've done previously. The first question says that the second term in a geometric series is 32 and the fifth term is a half. I want you to find A and to find OR. Then once you've A and OR, I want you to find Tn, the general formula for the sequence. Then I want you to find the smallest value of n for which Tn is less than 0.01. The fourth thing is to find S15. And the last thing I want you to do then is to find S infinity. Question 2 is a little bit different. It says that the sum to infinity of a geometric series is 9 over 2. And it says the second term is minus 2. And it says find OR. I've given you 2 pieces of information, and each one should allow you to come up with an equation with A and OR in it. And then you'll have 2 equations and 2 unknowns. You'll have enough information to find the value of A and the value of OR. So I want you to take this question down and just pause the video, work through it yourself, and then watch my solutions on it. Okay, in the geometric series, if they tell me the second term is equal to 32, I know that the second term is A multiplied by OR. And I can just say A by OR is equal to 32. I was also told the fifth term is equal to a half. The fifth term is A by OR to the power of 4. And I can say that A by OR to the power of 4 must be equal to a half. Now I've got 2 equations and 2 unknowns, so I can solve and find A and OR. The only way to do this one is to do it by substitution. So what I did was I took the first equation and I isolated my A. So what I did was I divided both sides by OR, and I worked out that A is equal to 32 over OR. And now I can rewrite my second equation, except instead of an A, I put in 32 over OR by OR to the power of 4 is equal to a half. There's an OR to the power of 1 on the bottom and an OR to the power of 4 on the top, so 4 minus 1 gives me 3. And I can say that 32 OR cubed equals a half. If I divide both sides by 32, I get OR cubed is 1 over 64. And then to get OR on its own, I just get the cubic root of 1 over 64, which is a quarter. So your OR in this case just works out as a quarter. And now once I know OR, I can sub back into this and I can find the corresponding value for A. If OR is equal to a quarter, I can say that A is 32 over a quarter. And a quarter goes into 32 128 times. So I know that A is 128 and that OR is a quarter. Now that I have the value for A and the value for OR, I can complete the rest of I can finish off the rest of this question now. Once you have A and OR, it's very straightforward to get Tn. According to page 22 in the maths tables, Tn for a geometric sequence is A by OR to the power of n minus 1. So in this case, I can say Tn is 128 by a quarter to the power of n minus 1. And that would be your final answer for part 2. Part 3 is probably the hardest part of this question. It says find the smallest value of n for which Tn is less than 0.01. In other words, I know the first term is 128. Let's just think about this for a minute. The first term is 128. If I multiply it by a quarter, the second term must be 32. I multiply that by a quarter, then I get 8. Then I get 2, then I get a half, and that's just going to go on forever. And I want to know what is the first term in this sequence that has a value smaller than 0.01. So mathematically, in order to calculate that, I want to know when is Tn less than 0.01. We've worked out in part 2 that Tn is 128 by a quarter to the power of n minus 1. Now what I would do is ignore the inequality and I would actually work out what is the value for n what is the value of n for which Tn is equal to 0.01? When I get that value at the end, I can then deduce whether I need to round up or round down based on the wording in the question. So what I would suggest here is I'm just going to let Tn, I want to work out what is the value for n when Tn equals 0.01. Here I've got one equation and one unknown, so I can solve it. Remember, in order to solve this one, we're going to have to introduce logs because the unknown is in the power. So I've readjusted my screen here and I've started up here. I'm saying that Tn is equal to 0.01. I want to find the value for n for which this is true. 128 by a quarter to the power of n minus 1 equals 0.01. I need to introduce logs because my unknown is in the power. But before I introduce logs, I have to isolate the part of the term that has the unknown, the part of the term to the power of n. So first I divided both sides by 128. I got a quarter to the power of n minus 1 equals 1 over 12,800. And at this stage I've isolated the quarter, which means now I can introduce my logs. I introduce ln on the left and ln on the right. Now remember, the reason we're introducing logs is because now we can apply the rules of logs. The third rule of logs on page 21 in your maths tables, in the middle column, it tells you if you have log of something to a power, you can just bring the power in front. So if I have log of a quarter to the power of n minus 1, I can just bring the n minus 1 in front. And now I'm happy out at this stage because there's no more powers. I have n minus 1 times ln a quarter, which if I multiply out, I get n ln a quarter minus 1 ln a quarter. Clearly my goal is to isolate the term with the n, so what I did was I added ln a quarter to both sides. And at this stage, in order to isolate n, what I want to do on this line is divide both sides by ln of a quarter. If I divide both sides by ln a quarter, I get n on its own. N is equal to ln 1 over 12,800 plus ln a quarter divided by ln a quarter. So when you plug all that into your calculator, your n works out as 7.8. So I've rounded that one off to the nearest decimal place. So that means I know the sequence started at 128, then 32, then 8, then 2, then a half. It's continuing on. And I know that after 7.8 terms, it would be, or I've rounded that one off to one decimal place, but roughly 7.8 terms, it would be at 0.01. Obviously, your answer needs to be a whole number here. I want to know when is it going to be less than 0.01. So I want to know when it goes further than that. So clearly, that means that if the 7th term would be bigger than 0.01. But then the 8th term would be the first one that is less than 0.01. So your answer in this case would be n equals 8. If I just continue this sequence on until the 8th term, it would be, that's the first number that was less than 0.01. I want you to be aware there, we could have actually just listed out the sequence and we could have got the first one, multiplied it by a quarter, and keep going. It would have been relatively easy there because I only would have had to do it 8 times. I only would have had to go as far as the 8th term. But overall, that's your final answer for this part of the question. Okay, for part 4, I asked you to get S15. To get S15, I just use my formula from my maths tables. I know that I'm dealing with a geometric series, so I know that Sn of a geometric series is a times 1 minus or to the power of n over 1 minus or. I already know a is 128, or is a quarter, and n is 15. So if I just sub them all in, I can plug it straight into my calculator, and the sum of the first 15 terms in this geometric series is 170.66666665. Now I want to purposely talk about this because when we do part 5, I want to compare our answer in part 5 to this one. I have 6 6s and then a 5. So what I want to do now is let's do part 5 and then let's compare our answer to part 5 to our answer to part 4. This is what you would get if you added up the first 15 terms in this geometric series. Let's see now what the sum to infinity works out as. So S infinity is an incredibly straightforward formula to use. I know that I can get S infinity for this geometric series because the common ratio, the absolute value of the common ratio is less than 1. In other words, the common ratio is between 1 and minus 1. The numbers are approaching 0, which means a sum to infinity exists. Once I know a and or, I can just sub in 128 over 1 minus a quarter. the sum to infinity, if you added up an infinite number of terms in this sequence, they would add up to 170.6 recurring. Notice in your calculator there you get a dot above the 6. That indicates that it's just 666, that it's just going on forever. It's 666, it's just a recurring decimal that goes on forever. But let's compare that to what we got for S15. S15 was 170, and then we had 6 6s and a 5. So it was incredibly close to this. I'm really close to this. Just the 7th decimal place, it's a 5 instead of a 6. But I want you to understand, this is kind of as we approach the concept of limits. Okay, as this series continues, by the time you get to the 16th number in this series, it's a really small number. You're adding on a number that is so small, you won't be able to get this 5 and you won't be able to turn this 5 into a 6. You're never going to get to 170.6 recurring. And the further we go, or the closer we get to that, the smaller the numbers in this series get. So if I got S of 100 or S of 1,000,000, again, there would probably be maybe 100 6s and then a 5. There'd be 0.666666 going on, maybe 100 decimal places and then a 5. You would get really close to the sum to infinity, but you'd never quite get there. So I just want you to make sure you understand the concept of the sum to infinity. The geometric series never actually reaches that number. It just gets really close to it. Now, there's only one more thing that I want to explore in sequences and series, and it directs related to your sum to infinity formula. So let's move on now to the next video. In the second question, I told you the sum to infinity of a geometric series is 9/2. And I told you the second term is -2. We can use this information to find OR. In fact, we can actually use this information to find A and to find OR. But in this case, it's only asked you to find OR. I've given you 2 pieces of information. And with each piece of information, you should be able to come up with an equation in A and OR. Then I'll have 2 equations in A and OR, and I'll be able to find the value of A and the value of OR. The first sentence says that the sum to infinity of a geometric series is 9/2. And I know from my maths tables that the sum to infinity of a geometric series is A over 1 minus OR. And I'm being told that that is 9/2. So I can actually just say that A over 1 minus OR in this scenario is equal to 9/2. Now I've got one equation and 2 unknowns. So obviously I need to come up with another one. The other piece of information I was given is that the second term is -2. We know from the start of this video that in a geometric series, the second term is A OR to the power of 1. And in this case, A OR to the power of 1 is equal to -2. So what I've written here now, I've got 2 equations and 2 unknowns, which means we could find the value of A and the value of OR. In this case, because A is multiplied by OR, we're going to have to use substitution to simplify this one. Before I worry about my substitution, what I think we should try and do is eliminate our fractions here first. In order to eliminate the fraction on the right, we would multiply both sides by 1 minus OR. If you multiply both sides by 1 minus OR, you get 9 times 1 minus OR over 2 is equal to A. Now, in order to eliminate the fraction on the left, we would multiply both sides by 2, in which case we would get 2A on the right hand side and the fraction will be gone on the left. 9 by 1 gives me 9, 9 by minus OR gives me minus 9 OR. So now at least we've eliminated the fractions. We should probably now worry about the substitution. What I want to do is isolate either my A or my OR. If I isolate my A, I can sub it in here. If I isolate my OR, I can sub it in here. But because we're only actually trying to find OR, it'll be easier here if we isolate our A. If we isolate A and then sub it in, we'll then have an equation that only has ORs. In order to isolate A in this equation, we would just divide both sides. We would divide both sides by OR. And we would end up with A is equal to -2 divided by OR. If I know that A is -2 divided by OR, I can substitute it into this equation instead of the A. So the left hand side would stay the same. It would be 9 minus 9 OR. And the right hand side is 2 times A, which in this case will be 2 times -2 over OR. And at least now I've got one equation and one unknown, so I'm going to be able to solve this to find the value for OR. Okay, so once we got to this line, I identified the immediate complication is the fraction. In order to eliminate the fraction here, I want to multiply everything by OR. 9 by OR gives me 9OR. Minus 9OR by OR is minus 9OR squared. And if I multiply the OR by the right hand side, the OR on the bottom will divide into the OR on the top. And 2 by minus 2 gives me minus 4. At this stage, we have an OR squared, we have an OR, and we have a number, which clearly means we have a quadratic equation. So what I did was add 9OR squared to both sides and subtract 9OR from both sides, and I end up with this quadratic equation. When we factorize it, we get 3OR plus 1 times 3OR minus 4. Now when you solve that, you get two values for OR. OR is minus 1/3 or OR is 4/3. The reason I wanted to do this question is that only one of these answers is valid. And I always do this in class, and students really struggle to identify which one is invalid. It's nothing to do with the signs. Often people will guess, oh, maybe it's because it's a minus. It's nothing to do with the signs. It's because there's a sum to infinity. If a sum to infinity exists, that means that the absolute value of OR has to be less than 1. Or in other words, it means that OR needs to be between 1 and minus 1. Now clearly 4/3 is not between 1 and minus 1, so that's an invalid answer in this case. So you only get one answer here. Your answer is that OR must be equal to minus 1/3. So that's all I wanted to talk to you about in this video. We can move on now and explore something different.